I think it's Scott. It's Scott. But you want to mute everybody? Mute everybody. Quickly. This is...
evening, everyone. Welcome back. It is our April Speakers Night for 2025. Welcome to RASC Toronto Centre. We are online tonight, and I am Dr. Elena Hyde, the second Vice President of RASC Toronto Centre, and this is our Speakers Night presentation. So please note that this is an online-only presentation and not at our new York University meetup location. So our President, Scott Masterton, we'll be talking about our various programs later on this evening. But first, of course, we have our main event to kick off. Just to get us started, I'd like to go ahead and begin with a land acknowledgement. The Royal Astronomical Society of Canada Toronto Centre meets on the traditional territories of many Indigenous nations, including the Haudenosaunee Confederacy, the Huron-Wendat, the Mississaugas of the Credit First Nation, and other Anishinaabe peoples. These lands are part of the Dish with One Spoon Treaty and are now home to many diverse First Nations, Inuit, Métis, and Indigenous peoples from across Turtle Island. As we engage in astronomy here together, we respect, learn from, and honor the deep relationship between Indigenous peoples, the sky, and the Earth. Now to get on to our main speaker event, I'm very, very pleased to be able to welcome Dr. Nadine Manset, Director of the Science Operations at the Canada-France-Hawaii Telescope. And of course, she has a lot of other titles as well. So she's actually been the resident astronomer for the CFHT since 1999, I believe, and is currently the astronomy group manager, the QSO manager, and the instrument scientist responsible for the spectropolarimeter, which has a little bit of a hard to pronounce name. I'm never sure if it's ESPA, so it's Espidons, but it's a wonderful, wonderful instrument, and I definitely recommend everyone to go and look it up later, or maybe we might even hear a little bit about it. I'm not sure. She's involved in a lot of outreach activities at CFHT, and she's the chair of the Maunakea Astronomy Outreach Committee. She has, of course, scientific interests around polarimetry due to perhaps that instrument, and she studies young stars of the T-Tauri type, astrobiology, spectroscopy, and optical and infrared imaging. So lots of wonderful research as well. And she's taught. She's taught in physics and astronomy at the University of Hawaii, and she was on the board of directors for the Canadian Astronomical Society, or CASCA. So as a scientist, astronomer, and educator, Nadine is the perfect person to tell us all about one of my personally favorite Canadian telescopes. And although I've yet to visit the wonderful place myself, it's something I'd love to look into. Nadine, please take us up, and away and tell us all about it.
Aloha, everyone. Welcome to this presentation. So I invite you to a journey through space and time with the Canada-France-Hawaii telescope. So once upon a time in Canada, about 50 years ago, astronomers wanted to have their own 4-meter class telescope to do their own research. They knew that the skies in Chile were very dark and clear, but they started to look for sites in Canada first. They even considered Mount Cobo in British Columbia. They never really arrived at a decision. It was kind of left in suspense. Meanwhile, elsewhere in space in France, French astronomers had the same idea. They wanted to have access to a 4-meter class that would allow them to observe the northern hemisphere. They already had access to at least one telescope, a smaller one, in Chile, in the southern hemisphere. They also looked for sites in France, didn't find any, and they decided to figure out what was the best site for astronomy on the planet. At about the same time, elsewhere in Hawaii, following the 1960 tsunami that destroyed part of the town on the Big Island of Hawaii, the Hawaii Island Chamber of Commerce decided to turn to astronomy and Maunakea to rejuvenate the local economy. The picture at right shows, in the background you see Hilo Town as it is right now. In the foreground you have a coconut tree, and you see the level of the waves of 3 different tsunamis that happened in the 50s, and in 1960. And in 1960, the wave rose to 15 feet, hence a lot of devastation. There was a node created in space and time that led to the creation of the Canada-France-Hawaii telescope. A tripartite agreement was signed in 1974. Canada and France decided to split the cost of construction, which is about $30 million, and University of Hawaii provided the infrastructures, for example, the road, to access the summit of Maunakea. Inauguration at the summit inside the dome of CFHT, that occurred in September of 1979, very quick construction phase. Maunakea is central to the story of CFHT, of course, and it is also central to the story of many native Hawaiians. Maunakea is an active volcano that was born about 1 million years ago. It is categorized as active, but the last eruption was about 5,000 years ago, so we're safe. For many native Hawaiians, they have ties to the summit. They have ancestors, for some of them, that are buried in the summit area or on the slopes of Maunakea. You see here a picture of a structure that is used for offerings and ceremonies. The picture at left, you can see some of the observatories in the background. You have Euclid, the UH telescope, Gemini, and then to the far right, you have CFHT, seen a few years ago. And this structure was established by the Royal Order of Kamehameha, and the picture at right shows a little, a bit newer version, seen from a different direction, and you can see the background. There have been a lot of studies of what one can find around the summit area and on the slopes of Maunakea. There are a lot of archaeological finds, there are burial sites, there are artifacts, and some of which are shown on this map. So this reflects the fact that Maunakea is very significant for the culture of many native Hawaiians. CFHT, like many other Maunakea observatories, is located on Maunakea, which is the land of the Kanaka Oiwi people. It's a mountain of considerable cultural, natural, and ecological significance to the indigenous Hawaiian people. At CFHT, we conduct all our operations with respect for the mountain. The picture that I show here is what I see when I leave my house. I live on the east side, on the slopes of Maunakea at an elevation of about 500 feet. I don't see the summit itself. I see the volcanic cones in the foreground, but every time I see that, I am reminded that I work and live on Maunakea. Maunakea is the best site for astronomy. Why is that? If you look at this satellite view of the Big Island of Hawaii, you see Waimea to the north, Hilo, the town that was often destroyed by tsunamis in the 50s and 60s, and Maunakea is kind of at the center towards the northern part of the island. If you zoom out, you see the Big Island with the other islands in the chain. Maui is the closest island to us, and then Honolulu is on the island of Oahu, which is a little bit further away. And if we zoom out again, at the center of the map, you see it's not high, it's Hawaii, the state of Hawaii, with the west coast of North America and then Asia on the other side. This is even more expanded view where you actually see the whole of North America and Asia. The interesting thing is when you look at what Earth looks like at night, and you realize that you can spot where humans live, you can spot where cities are, because there's a lot of light pollution. Because Hawaii is in the middle of the Pacific, we are far from those areas with high levels of light pollution. So let's zoom back into the Hawaiian chain. You see once again the Big Island. Honolulu, there's a lot of there's I think 1 million people who live on the island of Oahu, and Honolulu is a few 100,000. But the island is far enough that we are not too much affected by those city lights. If we zoom into the big island itself, you will recognize to the east Hilo. To the west, we have the town of Kona. And then the big round intense blob, that's actually the Kilauea volcano, one of the active volcanoes on the island. We are affected to a certain extent. From time to time, we do have to close our dome because we can detect that the level of dust particles of ash is a little bit high in the air, and we want to protect the optics and the equipment. So as a precautionary measure, we close the dome, we cease observations even if the sky is clear, until our sensors indicate that the level of dust particles goes down, which can take just a few hours. So why is CFHT on Maunakea, like other observatories? It's because there's very little city lights. The level of light pollution is relatively low, so the sky is dark. Here's another view of Mauna Kea during the winter. You see once again Hilo at the base of the mountain. First of all, Mauna Kea is at an elevation. The peak is at 4,200 meters. The mountain is high, therefore we have less atmosphere above our head to absorb the light of stars and to affect the observations. And then when we look at the profile of the mountain, we realize that the slope is very gentle, which means that the trade winds that come from the east just go over the slopes very gently. They're not chopped up by cliffs or abrupt landscape. It just flows gently. And this is also better for observations. We have less turbulence created by the relief in the terrain. So that's the second reason why Mauna Kea is the best site for astronomy, is because the atmosphere is very stable, which will create very sharp images. Here's another picture taken from CFHT looking north. So you can see in the background the island of Maui, the closest one. And then down below is the town of Waimea, where CFHT's headquarters are, where I am speaking right now. And what you notice, where are the clouds? The clouds are below the summit, which you can also see on this view, which dates from just a few weeks ago. Where are the clouds there below? There's an inversion layer that typically caps moisture and clouds well below the summit, which guarantees us access to a clear sky at night. So the high mountain provides us with dry atmosphere and few clouds. That's why Mauna Kea is the best site in the world for astronomy. That's why there are many observatories in the area of the summit of Mauna Kea. There are a couple that have been decommissioned so far, but all the others that are there are active, open every night when the sky is clear, and doing wonderful research. On this picture, you see specifically Subaru to the left, and then the two Keck telescopes, and then the NASA infrared telescope to the right. I mentioned that the tripartite agreement was signed in 1974, and then the telescope was inaugurated in 1979. That's 5 years. That is very short. CFHT was built in record time. And I'll show you a few pictures of the construction. Everything was built off-site, either in France or in Canada. Everything was brought in by plane, if it was a small part, but also by boat and by barge, assembled with the use of cranes. The picture on the left shows that the road, because of the elevation and the equipment, often the tractor trailer had to be pulled by an additional piece of equipment because it was kind of heavy. And the picture at right shows the dome once completed, but it hadn't been painted white at that point. The mirror was cast, and you can see here when it was inspected very closely with a lot of attention. After that, the mirror was polished, which is the picture shown at right. And after that, a small layer of aluminum was deposited to provide a mirror of 3.6 meter diameter to do our research. I believe this picture was taken around the time of the first light, so it has historical significance. This is a more modern picture of the telescope, and you have 2 or 3 staff members in the photo to give you a scale of the dome and the telescope itself. You recognize the yellow structure, which was in a previous picture, being trucked up the summit. That's what holds the telescope in place and allows us to move in any direction to observe whatever we're interested in the night sky. And with the telescope tilted on the side, you have another view of the telescope and the mount. Let's take a look at some of the discoveries that CFHT has made over the years. I'll start with the very first picture, what we call the first light, which happened in August 79, a little bit before the official inauguration. At the time of these first observations, CFHT was the 6th largest in the world. The picture shows the director then, who was Roger Querel, looking at the first picture. I'm not old enough to have ever handled photographic plates, but I know that in the 70s, astronomers used photographic plates. So when I saw this picture, I was quite intrigued because the director is looking at a film. I fortunately was able to talk to the chief engineer who was present in 79, and he explained that CFHT had ordered photographic plates, however, they did not arrive on time. Because we are in the middle of the Pacific, sometimes there are delays. Even nowadays, when we order stuff online, we have to add a couple of days to let the packages arrive. So that's what happened in 79. The engineers had to just figure out a simple camera, put it at the prime focus of the telescope, and that's what they used to take the first light picture. And here is this first ever picture taken with the CFHT. It's the globular cluster Messier 13, and it is only a 2-minute exposure, so quite short. This is a comparison of the first light image with an image that was taken decades later with a modern camera that uses electronic detectors called CCDs. You can see more stars, and with an electronic device, it's a little bit easier to produce color pictures, which then provides you additional information on the object you're looking at. The picture was taken with MegaCam, an instrument that was commissioned, first used in 2003. It has 40 detectors, and when it was first commissioned in 2003, it was the biggest compact mosaic for astronomy in the world. The field of view covered by those 40 CCDs is about 1 square degree, which it's not a coincidence, it's about the size of the photographic plates that CFHT was using in the 70s and 80s. And thanks to that big field of view, CFHT can do specific science research. We can look at objects which are nearby, maybe in our own galaxy, like a cluster of stars or a nebula. And those objects, because they're a bit closer, they take a big chunk of the sky, and we can image them sometimes with just one frame, one exposure with that big mosaic of detectors. If there's a nearby galaxy that fills the field of view about 1 degree by 1 degree, we can also image it quite easily with MegaCam. And the big field of view is important when we are not quite sure where the object we're looking for is located. And that is often the case for asteroids and comets that are discovered, not quite sure of the orbit, there's a big uncertainty. But if we have a big field of view, it increases our chance of finding those objects. So that's one of the strengths of CFHT with MegaCam. It's the big field of view of some of our instruments. I'll just go through a few pictures taken with MegaCam. Objects within our own galaxy, star clusters and nebula, where you can see on the right gas emitting light because it is heated by stars of different masses. And there's also areas that are a little bit more dark. Those are due to dust clouds. The dust is so fine, it's like smoke, but it's so thick, there's so much of it that you cannot see what is behind those dust clouds, and that's the dark patches in the sky. On the left is another example of a starry field. All those stars belong to our own galaxy, the Milky Way, and then the dark patches are small clouds of dust blocking, obscuring what is behind. You may recognize a picture on the right, which is a Andromeda galaxy with its satellite galaxies. You see a lot of details, stars, and then the beautiful dust lanes of that spiral galaxy. And this example shows one of the strengths of MegaCam. Not only there's the field of view, we also do processing of the images, which allows us to tease out very faint structures. When galaxies collide or even merge, this can create shells of material, gas, or stars, bridges, tidal tails. But these structures are really, really faint and hard to see and hard to get to unless you observe the right way and process the data in a very specific way. And this is what you can see on this image. Area of the sky, collision of galaxies, potentially, and that created all those strange structures that are filamentary and look like shells and warped tails. Recently, MegaCam was a major contributor to the Euclid space mission. That sounds a little bit strange, but before launching Euclid, there was a pre-survey to check areas of the sky that Euclid could study, and some of those pre-survey data involved CFHT. The data was actually taken with CFHT and then combined with the Subaru telescope, also on Maunakea, and another telescope also on Haleakala. Those images were crucial to the success of the Euclid mission, and that shows that not only can CFHT collaborate and offer complementary data to ground-based telescopes, we often also have ties with space missions. Euclid, also JWST, and even HST decades back. I mentioned that the field of view of MegaCam is very helpful when we look at objects we're not quite sure where they are. This is what happened in 2017 when we had our first interstellar visitor that was then named Oumuamua. On the left, you see a picture taken by the Pan-STARRS telescope, which is on Haleakala on Maui. The red bands show areas of the detectors that are not good, they have to be masked. The round points of light are stars, and then in the circle you see a very faint trail. That's an indication that there's an object moving not with the stars at a different speed, and that's typically an asteroid, can also be a comet. The astronomers from the University of Hawaii who took this image realized that just by the way the trail looks, it was a very unusual object, and they immediately requested follow-up observations from CFHT, which is shown image on the right. And in that image, in the red circle, the dot is the location of that asteroid. Additional data confirm that this object did not originate from our own solar system. It came from outside of our solar system. So this was the first interstellar visitor ever discovered and imaged. I mentioned the optical, but CFHT also has another instrument to take images in the infrared, and that instrument is called WIRCam. It was commissioned a few years after MegaCam in 2006. It is composed of 4 infrared arrays, and the field of view is a little bit smaller than what MegaCam can do. In the infrared, the technology often lags by a few years. So at that time, we were not able to cover a whole 1 degree by 1 degree field of view with those infrared detectors. To compare, you can see the Orion Nebula image at CFHT in the visible to the left. So you recognize the shape of the nebula with the dust lanes and the emission clouds, and the exact same location in the sky observed with WIRCam in the infrared. the object looks completely different. That's the beauty of combining visible and infrared. You get different perspectives, you get different information, you have access to different observations and different data. The stars that you will see may or may not be the same. You may see new ones in the infrared, especially since in the infrared you can kind of pierce through the clouds of dust and gas, so you can see more of what is hidden inside nebulas and star-forming regions. And here's another beautiful example of a nebula image with WIRCam. You see stars that belong to our own galaxy, and then at the center you have a nebula. You see emission, you see faint brown structures. Those are dust clouds that are associated with this region in the sky. In addition to taking images, at CFHT we have two instruments that can do spectral polarimetry. One is Aspidons, which works in the visible, in the optical. The other one is Spiro. Those instruments have a very small field of view, and in fact they only observe one star at a time, but they're very powerful. Either instrument can do straight spectroscopy, decomposing the light of stars into the different colors, the different wavelengths, and with that we can figure out the spectral type of a star, the temperature, the composition, the mass. If we're looking at a binary system, we can even discover or confirm exoplanets, which is something especially done with Spiro. In addition, those two specialized instruments can do spectral polarimetry. We have access to the polarization of light at different wavelengths. And polarization of light is a great way to get access to magnetic fields of stars. We can detect, we can measure the intensity of a magnetic field. And if we follow a star as it rotates over a few days, typically, we get a different perspective on the configuration of the magnetic field. This will leave an imprint in the data, and we can reconstruct a model and figure out if a star has a magnetic field that is very simple, a dipole, like a magnet, which is shown in a picture at left, or if a star has a more complex geometry of magnetic field, which is shown with the picture at right, with the loops, secondary loops that are smaller and go not only from one pole to another, but to different locations at the surface of the star. Spiro is one of our newest instruments, and it excels at exoplanet research. It can discover and confirm exoplanets, and we're starting to be able to characterize the planets. In some cases, especially if we have access to complementary data from other telescopes, we can figure out the mass and the radius of an exoplanet. And with that information, we can figure out the density. Is the exoplanet we're looking at rocky? Does it have an ocean? Or is it very puffy because it is a gas giant? And that was used for the object TOI 1452b, artist rendition on the left. It's a small planet. We think that it may entirely be covered by a deep ocean. That's amazing, amazing discovery. And in addition, in some cases, we can even start to be able to tell what kind of atmosphere an exoplanet has. To the right, you have an artist rendition of a different exoplanet, the hot Jupiter Tau Boötis. And in this case, we were able to get a snapshot of the atmosphere. We were able to find carbon monoxide, I believe. And the astronomers were expecting water, but didn't find any. As is often the case, you look for something, you're pretty sure what you're going to find, and then it's not exactly what you expected, so it generates additional questions, and you are still observing that object to try to figure out what it is made of. Spiro is a very powerful instrument, also when used in parallel with Aspidons. Our fifth instrument that we are currently using is called CITEL. CITEL combines the best of both worlds. We can do images and spectra at the same time. Instead of taking just one image, we take a cube of images. CITEL is basically an interferometer, and when the data are processed by specialized software, the cube of images becomes a cube of images, and each image represents a different wavelength. So we can look at the whole image, for example, a galaxy, like what is shown here, at a specific wavelength, and, for example, figure out where are stars forming. You can look at the morphology of the galaxy and locate within spiral arms, for example, where star formation is happening by looking at the image. And then once you have found an interesting component in your galaxy, you can take just that little pixel on the image, go through the cube, and you will get the spectrum for that region in the galaxy. It will typically show emission lines at different wavelengths, and then you can reconstruct composition of the region you're looking at, or the dynamics, because you have access to velocity information. Here's an example of a map that shows the velocities in M51. So it's a spiral galaxy, and there's part of the galaxy which is receding from us, and then part of the galaxy which is going towards us. We also have this last example. It's an object within our own galaxy. So it's a veil of filaments from a supernova remnant, and the different colors were color-coded to indicate the composition or the specific wavelength we were looking at. So H-alpha, oxygen, and sulfur. So you can see that different areas of the nebula have a different composition and a different shape. Thanks to all those engineering and technological innovations, CFHT has remained at the forefront of astronomy. We have done more than just engineering and technology hardware innovations. We have also looked at processes to try to get the best science possible. And we've done that with what we call QSO, or the Queued Surface Observing Mode. So once upon a time, astronomers came to Hawaii to perform their own observations. So that's what we call the classical mode, and that's what we were using until about 2001. Principal investigators of a specific program receive typically one night, sometimes maybe two, and the success of each of those nights depended on, well, the PI arriving safely and on time in Hawaii. They had to carefully plan what they were going to observe during the night. You would hope that at the summit, 4,200 meters, with only 60% of the pressure or the oxygen at sea level, that they wouldn't suffer too much. It does have quite an effect physically, and it's harder to think at the summit. To be successful, the observations have to be efficient, no technical issue, and good weather. Then the PIs would go home with lots of good data. They could publish papers and be successful. But from time to time, it snows in Hawaii to the point that the sky can be super clear, but there's ice on the dome and it's not safe to open it. Or you can go to the summit and you're completely sucked in, 100% humidity, you cannot open, you cannot do anything. So if you're an astronomer and you had one night and you're not lucky, you go home with no data and you have to reapply for time. So you have to wait a year before your second chance. In 2001, we started using the QSO mode. So there's two components to that mode. There's the service part. So service observing means that the PIs don't travel to Hawaii anymore. We perform the observations. We have a team of highly trained observers to do that. The Q part of the QSO mode means that the PI tells us all the information we need to be able to observe for them. So information about the target, the name, the coordinates, either a galaxy or a star, the instrument configuration, so which instrument, if it's one of the imagers, what's the filter, and what is the exposure time in each of the filters? What are the sky conditions? Does the moon have to be set with the sky very dark, or can the observations tolerate a little bit of moon? We can time observations very precisely. We can observe exoplanet transits. If we have to observe something at 2:05 in the morning, we will start it at 2:05 in the morning. If we have to follow a star when it rotates, so we can map its magnetic field, and let's say that we have to take 50 observations over 3 or 4 months, we can do that. Do one observation every night, spread out over a few months. And this is thanks to a team of highly trained CFHT coordinators, resident astronomers, who decide what to observe and when. So we have local team of highly trained observers. We know which programs are more scientifically valuable, so we always start with those. So we have priorities. We match the programs with the sky conditions that they need to do their science. We take the best calibrations because we know our instruments very well, and we do all of the data processing, which saves time for the PI. So we get more data and better data, which increases the efficiency of our observations. In 2011, we moved to a single person remote operations mode. So one person observes from Waimea, not from the summit, and takes care of checking the weather, monitoring the situation, checking the sky, making sure the facility is healthy, there are no technical issues, no error message. They take cues prepared during the day and then send the observations. They look at all the exposures taken to make sure there was no technical issue during the night, and then they track everything and log everything so that somebody during the day can look at that and make sure that everything was fine. All those successes start with people, with the CFHT staff, whether it's engineers or people who work with the software, people who observe, people who prepare observations. This is a picture from a few years ago. You can kind of guess what year, given that everybody is wearing a mask. This was during a activity at the summit to redo the coating of the primary mirror. We have engineers, we have technicians working in Waimea or working at the summit, and even at the top of the dome. There's maintenance we have to do there from time to time. We need a safety officer to make sure people have harnesses and ties if it's needed. We have mechanical engineers, software engineers, electronics engineers, detector engineers. We, of course, also need receptionists. We need somebody for payroll because we want to be paid every 2 weeks. We need a car mechanic, a safety officer that I also mentioned. So it's not just astronomers. The majority of the staff is actually not astronomers. We have 7 astronomers or engineers which are provided by Canada or France of Hawaii. And since 1999, we've always had 3 Canadian resident astronomers, and those are shown here on this picture. So we currently have, there's myself, I've been here since 99. We also have Daniel Deveau at the top in the middle. And just a few months ago, Viraja Katu arrived also from Canada. People stay typically for 3 to 6 years. Astronomy's future has to include community astronomy. People are very important. We can't do astronomy, build telescopes and observatories like we were doing 40 or 50 years ago. There's a concept of community astronomy which is being talked about more and more by the astronomers in Canada, by astronomers in the United States. The definition is not clear necessarily, and the vision is still a little bit fuzzy, but we know that it means that we have to actively involve local communities, non-astronomers, people who live in the community where those observatories operate. So I'll show you 3 examples. Ahua he inoa means calling forth a name. This is a program that was started by the Imiloa Astronomy Center in Hilo. And with this program, native Hawaiian students name objects that were discovered on Maunakea. Astronomers explain how the object was discovered, with telescope, with which instrument, what the object looks like, what type of object it is. And the students take that information to look at the Hawaiian language and try to find words that could characterize or express something about the object. And this is how Oumuamua was named when it was discovered in 2017. Oumuamua means messenger from the distant past. Another example is Povehi. That object did not involve CFHT. It used submillimeter facilities on Mauna Kea, the James Clerk Maxwell Telescope and the submillimeter array. It is a black hole at the center of a galaxy. So you see, well, you don't see, there's a black hole at the center, and then there's a ring of light, matter falling into the black hole, and because of the gravitational field, this image is distorted and just forms a ring. That was named Povehi. Po means night or darkness, and Vehi is like the garland of light around the object. That's why it was called Povehi. There are other objects that were named with a Hawaiian name. At CFHT, we are also starting to include Hawaiian language and culture in our day-to-day operations. So we have a project of using espadons and SPEW at the same time on the telescope. We want to mount them at the same time on the telescope and get data in the optical and infrared at the same time. Initially, the project was known as Vision, and then we called it Venaukeao, which means the first glimmer of light before sunrise. And more recently, we fabricated and installed a camera near the summit of Maunakea that looks upward and records clouds. It's a cloud watcher. The natural name for that instrument is Nana'au. Nana means to see. Ao is what we call a cloud in Hawaiian. We are starting to incorporate the culture and the language into our culture at work. Second example is the Maunakea Scholars Program. It is a program that was started at CFHT, and since 2015, we have reached out to over 1,000 high school students from public schools, over 10 high school through 6 of the islands in the States, basically the 6 main islands. Some of those students have obtained time on some of the telescopes on Mauna Kea. So CFHT, Keck, Gemini, Subaru, NASA Infrared Telescope. They are using those powerful instruments and observatories to carry their own research that they present them at career fairs. We've had, we're starting to see some students actually go through astronomy programs and then get a bachelor's in astronomy. There's even a student who is now herself a science teacher at high school, and she is now enrolling her own students into that program. So that's a way to incorporate locals into what we do. We share our instruments. Finally, there's now the beginning of a new model of doing astronomy on Mauna Kea. In 2022, the governor signed into law what we call Act 255, which established the Mauna Kea Stewardship and Oversight Authority, what we call MKSOA. This law is charging MKSOA with being the primary state agency responsible for managing all the activities on Mauna Kea. Up until MKSOA, University of Hawaii was managing activities, so astronomy, but also permits for commercial tour operators, filming permits, research regarding the fauna, the flora, the archaeology. There's a rangers program to maintain the safety on the road. So that was taken care by UH. And in 2028, MKSOA will have to manage all of that. And what is interesting is MKSOA is led by a board of 12 members. And some of those members, there's one member who has to be a lineal descendant of a native Hawaiian practitioner or elder. There's a seat for a recognized practitioner of the native Hawaiian culture. We also have a expert in education, and it happens to be that this time right now, that person is also a Hawaiian cultural practitioner. We need somebody knowledgeable about the management of the land, especially land on the Big Island specifically, and land on Maunakea. There's a member which is nominated by the State House of Representatives, and this happens to be also a Hawaiian cultural practitioner. So right now there are at least 4 that are native Hawaiians and have very strong ties with the culture. And then in that board of 12 members, there is 1 representative of Maunakea observatories. Activities on Maunakea, including astronomy, belong to everybody and are going to be managed by everybody, people from different areas of society. I will leave you with this Hawaiian saying, Ikawa mamua, ikawa mahope. And this can be loosely translated as the future is in the past, so learning from the past will guide our future. CFHT is a facility that is over 45 years old. We have a lot of experience and expertise in astronomy, engineering, technology. We have ties with the local community. We have learned what works, what doesn't work. And with that knowledge, we want to build a better future for astronomy on Maunakea, a better future for everybody, not only astronomers, but also our local community. I thank you, and I'm open to any question that you may have.
Thank you very much, Nadine. This has been a wonderful talk, as I knew it would be. I love how you incorporated the community astronomy there, and it does sound very much like things are looking up at Mauna Kea and at CFHT in particular. Wonderful telescope, and obviously such great history. We do have a few questions coming your way over from YouTube, so we'll see how many we can pass over to you successfully. So our first question is sort of a question in the form of a comment, which I guess as scientists we've seen a lot. So this was a question about, so there's a guy who's actually a Hawaiian snowplow driver. So the snow management on the mountain.
Yes, it snows in Hawaii. It's incredible, but it snows on top of Maunakea. And there we have a snowplow. We also have trucks with a blade in the front when there's not too much snow. And whenever it snows, the staff taking care of the mountain has to close the road and then send the snowplow to clear up the road. And sometimes during blizzards, the snow falls fast enough that as soon as they're done, they kind of have to start again. And that's what we know, that there's no real chance of us observing, because too much snow falling too fast, and we know we're going to lose 2, 3, 4 consecutive nights because it's winter.
Yeah, I guess that's what a little altitude will do for you, I suppose. Very, very interesting stuff. Now we have another question coming in from, it looks like Zapfan. Do the people on site use supplemental oxygen?
Not at CFHT. However, I know that other facilities have little portable oxygen bottles with a little cannula to help them work up there, because especially if they're doing physical work, that's even more demanding, and that helps. So it's provided for some of the staff.
Wonderful. Well, I'll keep that in mind, I suppose, if I ever get a chance to go up that way. Now we have another question, looks like from the same user. Any news on the TMT construction? So switching to a totally different telescope.
Okay, so I'll share what I know, which is not necessarily the whole story because I don't work with them. Right now, they are paused because they have requested the American NSF, the National Science Foundation. They've asked the NSF for additional funding because they need more money to build the TMT. And a requirement of the NSF process is to do community consultation. And there were hearings, people were able to submit testimonies, and there were so many testimonies submitted that the NSF is still looking at them. So they're going to look at those testimonies to see if there's a good relationship between TNT and the local community, and see if it's worth funding the TNT. The thing is that astronomers want the TNT and another similar telescope in elsewhere on the planet, and both facilities need additional funding, but it's not clear if the US government or the NSF will have enough money to fund both. So then if there's a choice that has to be made, things have to be looked at much more carefully. This being said, people are not idle at the TNT team. They have been working on designs, and since the TNT is a design with a segmented mirror, a lot of the segments have already been cast and even polished. So they have already started to build part of the mirror. There's quite a long ways to go, but that part of it is already in motion.
Wonderful. That's, I suppose, something to keep an eye on. There's a lovely comment from Polaris Starman that just says, thanks for the clear, comprehensive description. And we have, it looks like, one more question from, this is from Brian, who has a similar question about Maunakea. Are there any new telescopes being planned on Maunakea? Maybe not the TMT.
No, there aren't. There's, besides TMT, there is no other new facility that is going to be built. And actually, the plan for the future is to decommission some telescopes, and already two have already been decommissioned. There was a small telescope for University of Hawaii at Hilo. That one has been decommissioned last year. There was also a sub-millimeter telescope that was also dismantled, and the telescope itself is going to be moved to a different site in Chile, I believe. So it's going to get recycled. But the structure itself, the dome, that has been dismantled and the site restored as much as possible, like what it looked like before construction. And eventually, the plan, this is something that MKSOA has to think about, is to make clear how many telescopes should be allowed on Maunakea. So this is to come. This is going to be discussed in the years to come.
Wonderful. Looks like that's most of the questions that have come in. Of course, I get to sneak in one quick one of my own. I was just wondering, since you were mentioning the spectropolarimetry earlier, is there any plans to say what's going to happen in the next couple of years with that?
We are going to keep doing the same type of science, and because we're working on the combined instrument Venao, this will require work from the software point of view, because usually we use one instrument at a time. So how do you use two at the same time to take two exposures at the same time? We have to figure that one out, and also help observers how to launch two observations at the same time, how to plan a night when you're basically planning two things at the same time. So this is an ongoing project, but once the instrument is available and functional to do simultaneous observations, we're going to continue to do the same type of science, exoplanets a lot for SPU, and then also more standard spectroscopy, looking at stars of different spectral types, different masses, and different temperatures.
Wonderful. Well, thank you very much for joining us this evening, and it's been absolutely great to have you on. I'm sure we could stay here talking quite a while about telescopes and fun software things, actually, but we'll have to wrap up for now. So I'm going to go ahead and send over to the final transfer for the evening. Those of you who've been here before know what's going to happen next. That's right, we're going to do one last switch, and we're going to hand over to our president of the Toronto Centre, RASC, Scott Masterton, to finish off the evening. Over to you, Scott.
Yes, thank you, Elena. And I couldn't help but think about my time on Maunakea as Dr. Manhasset was telling us about the telescopes there. In 2012, my wife and I flew to Hawaii to view the last portion of the transit of Venus. And we did that with some other members of the Toronto Center. And the highlight of that trip, notwithstanding the viewing of the transit of Venus, was we went from 9,000 feet to the top at 14,000 feet for a tour of the Gemini telescope. But the vivid part of that was the road up. And it was about 6 miles, 5 of which were probably the worst road I've ever been on. And we were fortunately in a rover. The last mile, though, is perfectly paved, so as not to raise any dust. And I do recall getting a oxygen sensor on my finger for testing, and some of our members did require the supplemental oxygen. So that was my memories of Maunakea. So now I want to speak to you about the announcements, and we're going to have some announcements. There we go. So I want to explain to you that we have two types of meetings. You've just experienced the speakers night, which is online only, and was really very interesting. The other event is 2 weeks from now, and that'll be a RAN, or a recreational astronomy night, and that is in person and online. And of course, the RAN features our members talking about their own scientific astronomical investigations, and you do get information about the upcoming events for that month. And also on those coordinated with those meetings, you can do a tour of the Carswell Observatory every Wednesday evening during the winter. And you just need to only go to the website there indicated, and obtain a ticket, which is free. And if you have any questions, you can speak to Elena or write to Elena at her email address. I'd like to let you know about DDO, the David Dunlop Observatory Global Star Party for International Astronomy Day. This is an event Saturday, May 3rd. 2 episodes, 7 to 8:30 and 9 to 10:30 at the David Dunlop Observatory. And it'll be a live stream event with which the observatory will be participating, and others will be participating. Access and fees are as indicated and can be found at the RASCTO.ca. Millennium Square, free public star party, May 2nd or 3rd, depending on the weather. Go there to view the sky and safely view the sun at 6 and 8 p.m. The go, no go decision will be made, so keep an eye out for that. This is a free event. Then we have Recreational Astronomy Night, our next one, May 7th, at York University, and this will be in person and online. Andy Beaton will be delivering the sky this month. Dennis Gray, occultations, and Ed Trajas want to be left in the dark. I wonder what that'll be about. Why don't you tune in and find out? And of course, after that meeting, York University also hosts a public weekly stargazing at the Arboretum parking garage. Get more information and times from the York University Observatory homepage. City Star Party, Bayview Village Park in May. And here again, this is open to members to view on members' telescopes. And this is May 5th through 8th. Monday, Tuesday, or Thursday, and a go, no go decision will be made just before the event. Go to rastos.ca to get information there. Our next speakers night, May 21. This is going to be very interesting. Dr. Ethan R. Siegel, theoretical astrophysicist and science communicator. He's going to tell us about the James Webb Space Telescope. You'll recall that telescope went up, and we were all on tender hooks while it opened up and accomplished its 300 points of failure successfully. Um, the DDO Sunday Stargazing, May 25th, 2025, and registration information is there. You get to view the sun safely. And of course, for members, the Carr Astronomical Observatory is open and available year-round now. Masking is optional. Go to the bookings page to sign up for and find out availability. And of course, you have to be a member in order to do that. And we would encourage you to, if you're interested, to sign up at the National Office mempub at rasc.ca. And of course, once you're a member, you can volunteer, and we'd love to have you. We run on volunteer energy. We may not pay you, but you'll certainly get a very interesting experience. And a fun fact, why do the oceans have tides? Well, it's because of the moon and the sun. The gravitational pull of these two objects make the water on Earth bulge, and as the Earth turns underneath, we get tides. That's why we get a high and a low tide every day. So I want to say to you, have a good night. Thank you for joining us, and be safe. Keep looking up.